Okay, I want to talk about what happens in the case where we start off with multiple random variables. And so we're going to assume that we've got x1 and x2 are jointly continuous, which means that we have some joint PDF for them. And we're going to take these two new variables to be functions of the old ones. Right? So y1 is going to be some function of x1 and x2, y2 some function of x1 and x2. Right, so g1 and g2 are two distinct functions here. y1 and y2, two distinct new random variables. And the goal here is to find the joint PDF for y1 and y2, which we're going to call f, lowercase f sub y1, y2. Now over on this part of the board here, I've just recapped everything we talked about in the last video in the single variable case where we start off with a single continuous random variable x, and we've got some other random variable y, which is a function g of x. Well, then we know that we can calculate, and this is just a rephrasing of the sort of punchline of the last video, we can calculate the PDF of y in a relatively nice way. Right, this is effectively what we're saying here. And what I've done is just replace the a that was in here, which is a y value, by just calling it g of x. Right? And what we're saying here, once we know that g is invertible, every y value can be written as g of some x value. And so rewriting it in this somewhat strange looking way, right? It looked good enough the way it was before, so why do this? The reason why is that in the multiple variable case, this is actually going to be a more convenient way for us to think about it. All right, so we had these two conditions that we needed our function g to satisfy. We needed to know that g was invertible so that we could even talk about the inverse, which was what the entirety of the last video was about. And we also need this denominator down here to not be 0. And so one way of phrasing this is just to say that g prime of x should never be 0. That's a very simple way of saying it. In the last video, it was a little more complicated looking. It said that g prime of g inverse of a shouldn't be 0. It's effectively the same thing, just using the invertibility of g. All right? And somehow these two conditions are going to be what we want to translate to our new scenario with multiple variables. It's just going to be a little more complicated, obviously, because there's a lot more going on. And as I mentioned in class, just doubling the number of variables from, in this case, 1 to 2, or if you think of y and x separately, 2 to 4, you're not really doubling your work. It's more like you're squaring the amount of work you have to do. All right, so we just have to be a little bit careful, a little bit diligent, and use some things that we saw in Calc 3 that are going to help us here. Okay. So, how does 1 translate? All right, so here our first point was that g had to be invertible, and that translates, we just have to be a little bit careful about what invertibility really means. It means that y equal to g of x has a unique solution, x, for every y. All right, so we need the same thing to be true here. All right, so we need the system. Oops. We need the system. Y1 equals g1 of x1, x2, and y2 equals g2 of x1, x2. This should have a unique solution, a unique pair, x1 and x2, that solves this system for every pair y1, y2. So this must have a unique solution, x1, x2, for every y1 and y2. And again, when I say every y1 and y2, I mean every y1 and y2 that we care about. Right? There are, in certain contexts, going to be outputs here that we just don't care about. Right? If In the one variable case, if we were looking at, say, a log normal variable, so x would be normal, g would be the exponential function, and y would just be e raised to the power of x, well then we don't care about negative y values, right? It doesn't make sense to talk about those. So this first point here is really just saying that there's going to be a unique solution to this system, right? So if you give me some y1 and y2 that are valid for us to consider, I should be able to take this system and solve it to tell you exactly what the single solution, the unique solution, which is a pair x1, x2, is going to be that when plugged into g1 and g2 outputs y1 and y2. Right, this is what this means. And it's the same idea as invertibility in number 1 here, but it is just a little bit more complicated, which makes sense because we've doubled the number of variables. So, we want to talk about the analog of 2 next. And to do this, what we really have to do is think about what does it mean for, here we only have one function g, and it's relatively easy. It's a Calc 1 problem to talk about its derivative. There's only one derivative, right? There's only one first derivative, and so it's relatively straightforward. Here we've got two functions, g1 and g2, and each one of those have two distinct first derivatives that we can talk about, right? Each one of g1 and g2 has a partial derivative with respect to x1 and a partial derivative with respect to x2. So we need to figure out how 2 translates. Right, so the analog of 2 really what we need to do is figure out a way, sort of a coherent, logical way to talk about a first derivative for this pair of functions g1 and g2, which depend on a pair of variables. So we need just one clean statement about something that we can call a first derivative, a single first derivative of this pair of functions that depends on a pair of variables. Right? Again, keeping in mind that each one of the 2 functions has 2 first partial derivatives. So the way we do this is called the Jacobian. This is the Jacobian of g1 and g2. All right, so essentially what we do is we take every possible first derivative of these 2 functions with respect to their 2 variables. Right, in other words, we're going to take the partial of g1 with respect to x1, and then we've got another first derivative of g1 that we can consider, the partial of g1 with respect to x2. And now we do the exact same thing, but for our second function, g2. So we've got a partial of g2 with respect to x1, and we've got a partial of g2 with respect to x2. And now what we do, we've got 4 distinct quantities here, and as I just mentioned, we want a single clean statement like this one, right? A single statement that somehow summarizes or condenses all 4 pieces of information that we get here into just one expression. The way we do that is by taking the determinant of this 2x2 matrix. All right, this is what we're going to call J of x1, x2, the Jacobian, the so-called Jacobian of this pair G1 and G2. All right, and let me get rid of this. Hopefully we've got that down by now, right? This pair G1, G2 has to be invertible is effectively what 1 said. And this Jacobian, right, if you remember how to calculate 2x2 determinants, right, you multiply along the diagonal. So this turns into the first derivative, the partial derivative of g1 with respect to x1, multiplied by the partial of g2 with respect to x2. And now we subtract the multiplication on the off diagonal. Right, so this is going to be minus g1, the derivative, the partial of g1 with respect to x2 times the partial of g2 with respect to x1. All right, so we get a statement like this one. Now, the claim here is that this Jacobian somehow, it somehow incorporates all four of the possible first derivatives of our pair of functions, which depends on a pair of variables. And now, it's all in one line here, right? This is just going to be some quantity, right? This is no longer a vector or a pair of things. This is now, if we put in an x1 and x2 value here, we're going to get numbers as outputs. We're going to get 7 or -30, right? We're going to get answers here that are just concrete numbers if we plug in concrete values. And so the analog of 2 in the single variable case, now in terms of the Jacobian, is relatively easy to write down. Here we wanted a first derivative to not be 0. Here we've got this sort of fancy analog of a first derivative. Well, the exact same thing should be true. We just want it to not be 0. So that's the requirement that we put on this. Right, so our new requirement, our new second requirement, is going to be that this Jacobian is not equal to 0 for any x1 and x2 that we care about. All right, so on whatever domain you're considering this, whatever range of your jointly continuous random variables x1 and x2 are, whatever that range is, this Jacobian should be non-zero on that entire range, right? Or equivalently restated, it should be non-zero on whatever this domain of g1 and g2 is. All right, so it should be non-zero, and that's the exact equivalent, right? That's the analog, I should say, of number 2 in the single variable case, just generalized to the multivariable case. Okay, now let me keep this statement here about single variables, and let me just say what happens in the multivariable case. And this is really a consequence from Calc 3. All right, so in Calc 3, we've got this, we go through the exact same procedure as in the single variable case. We consider the joint cumulative distribution function for y1 and y2, these new random variables. We rewrite them in some way as integrals that relate back to x1 and x2, and then just like in the single variable case, we basically use a fancy implementation of the chain rule. Right, that's really what's going on here. And in Calc 3, or you could think of it as a fancy interpretation of the implementation of U substitution. And that's exactly what's going to happen here, except now instead of saying we need Calc 1 for it, well, now it's multivariable, so we need Calc 3. And the way this works is as follows. All right, after rewriting all of this as an integral, this thing would be a CDF, and it would turn into an integral, which we would then differentiate to get back to the PDF. And again, in the multivariable case, it would actually be a second derivative, right? It would first be the derivative with respect to y1, and then with respect to y2. So all of those details omitted, what we end up with is this. We get the joint PDF of f, right, just like we had before, and we divide that, just like here, we divided by the first derivative. Well, the analog now, right, we no longer have just a single first derivative to talk about. What we have instead is this Jacobian. All right, so what we do is divide by the Jacobian, which we know by this assumption shouldn't be 0, which means that it's okay to divide by it. And the analog of taking plus or minus here is effectively just putting that thing in absolute values. All right, so this is what we end up with here. We can rewrite our PDF, or rather we can calculate our PDF, our joint PDF for y1 and y2 in terms of the original PDF for x1 and x2, and this sort of fancy version of a first derivative for multiple variable functions, which we call a Jacobian, and we just divide by that and take the absolute value. All right, so this is how this works. In the next video, I'm going to go through a quick example, a relatively simple example, of how this can actually be implemented.